All right, welcome again to Control Systems, ECE 3004. In fact, it's 2002. Let me make that clear. 2004, 3004, ECE 3004. All right, that's Control Systems. And I trust that you can see the outline.
Yes, sir.
Great. So the first unit, session one, first unit, unit one, has to do with the introduction of control systems. And they should take us about 2 sessions. So this week and next week, perhaps, if it is that we're able to complete the lecture today, then so be it. But we are going to sort of intersperse the lectures and the tutorial sessions. So this particular unit may take 2 weeks. That will include a tutorial session. All right, 2 weeks in fact. The other unit, that's unit 2, is concerned with mathematical modeling and mathematical modeling. And in this unit, maybe I should go to the actual all right, are you seeing unit 2 now? So unit 2 is concerned with mathematical modeling, and essentially in this section we'll be looking at how we can derive mathematical representation for physical systems. And so this will take about 2 sessions. All right, session or unit 3 will be concerned with state space modeling. Again, we're still into modeling, but a different type of modeling. So units or sessions 2, 3, 4, and 5 will be concerned with mathematical modeling. Just confirm that you're actually seeing unit 4 at this time. Are you seeing that?
Yes, sir.
Beautiful. All right, so unit 4, control systems, characteristics, and performance analysis. I'm going to remove this midterm test situation here, so don't pay this any mind. I'm going to remove it. All right. Unit 5, root locus. Unit 6, frequency response method. And these are methods used to analyze control systems. Same for frequency response here. And then the last unit, unit 7, we'll be looking at the design of control systems. That, in a sense, will cover the module control systems. All right, basically the summary of the content that we'll be covering. Now, as it relates to the teaching learning approach, lectures and discussions, that is online lectures and discussions now, would be the means of covering the content, and you'll also be doing laboratory exercises. The details as it pertains to how the labs will be conducted, I'd have to communicate with you within this week or early next week. If it is that you are required to come in on campus to do laboratory exercises. Apart from that, you may be required to do some simulations remotely. All right. Assessment. There will be, I should say, 4 tests. So there's no final exam. 4 tests, and you'll see a breakdown for each of the assessment pieces. 10 in the first instance, and 20 in the second and third instance, and the final test is 30%. The laboratory exercise will account for 20% of your total grade. All right. These are some tentative laboratory exercises. As I said before, the final detail will be worked out in the next couple of days. Textbooks, I don't know, persons never normally over the last few years, been purchasing books. However, persons may be able to find these books by other means, and certainly if you can, then certainly use it to your benefit. The library would have had a number of these books on the shelf, but with the current situation, I'm not sure if persons are going to go on campus to access the library. And the frank truth is, persons never normally go to the library that much to access these books. But just letting you know, these are the books available, and if you happen to be on the campus, you can always go on into the library and source these books. Otherwise, you can use other methods if you are, if you can borrow it, or you can find a soft copy. All right. But in addition to that, all the content, let me be clear on this now, all the fundamental content will be provided on the platform in the form of lecture slides and reading notes. Okay. Any questions on what I've just covered here?
Is there an estimation, sir, in like when will the practical classes begin?
All right.
For the labs?
It will not be for this week. I'm going to have dialogue with Mr. Holgate tomorrow, all things being equal, and we will finalize those arrangements. But let me see. I don't have it on this, but when do you have labs again? I think one's on Thursday. Thursday. Could you remind me your lab time?
Sir, I have Monday, sir.
Monday, sir.
Mondays?
I have Monday.
Only?
Yes, sir.
Have Monday
No,
to
sir, I have it on a
Thursday.
Thursday.
Well,
On Thursday?
12
Yeah, no, I
p.m.
saw one for Thursday. I think there are about 3 lab sessions, but anyway, let me work with what I hear so far, Monday and Thursday. So the persons who have Monday sessions, they wouldn't have had a lab, right? And so for the persons on Thursday, there'll be no lab this Thursday. As I said, I'll have dialogue with Mr. Holgate, and then we'll finalize the lab arrangement. All right?
Sir.
Is there a question?
Yes, sir. If I mentioned
All right, hold on. Because of some feedback issues, I'm just going to ask you to use the raise hand feature. I'm going to have to bring up this section so that I can acknowledge you. All right, and the other persons, you just kindly mute your mics so that we can minimize the negative feedback. All right, go ahead, Johnson.
Yeah, I'm not sure if you mentioned it already or if you intended, but will there be any face-to-face labs or will everything be strictly online?
All right, it just came on. The details of the lab arrangement will be discussed or will be communicated to you by, in fact, before the weekend closes or before the weekend starts. So by Friday, I'll be able to confirm it with the group what the lab arrangements will be. Okay? Any other concern or questions related to what we have discussed so far? All right. So I'm now going to move into the presentation for today. That's lecture number 1, which is already available on the platform. All right, so let me bring this up. All right, so here I'm bringing up the most current version of the slide. So we have multiple presentations. All right, this one should do it. Let's try this again. All right, good. Okay, so today's lecture is entitled Introduction to Control Systems. And let me it's a little bit different from the previous Blackboard. All right, I'm going to go right to the file and share it from there. All right, so in this presentation, I'll be covering what a control system is. I'll be looking at some examples of control systems. We'll look at the importance of control systems, types of control systems, and the components of a control system. So, question could be asked, what is a control system? And the simplest definition that I could present would be this one. All right, so a control system is a group of components working together to provide a desired response. All right, so in this definition, there are some keywords I want to bring to your attention. And what I want to ask, I'm not able to see the raise hand feature now, but if you could just perhaps open your microphone and tell me what word it is. If you were to take one word from this definition here, all right? One word or two words, let's put that two words. What would those two words be that would capture the essence of what a control system is? Can you just open your mic? I'm gonna try it now.
Working together.
All right, so here's myself working together. Anybody else? So,
Desired
well,
response.
those are your two words, right?
Yes, sir.
All right, working together. Anybody else?
The desired
Components working.
coordination.
All right, noted. Anybody else?
Yes, the desired response.
All right, so let me share with you what I would love for you to take from this. You could go ahead and mute your mics. When we speak about a control system, we're talking about the desire for a certain result. So regardless of the nature of the control system, where you find it, it is always going to be the same. There's a desired response, right? There is a desired response. So I want us to bear that in mind as we think about it. It's a desired response. And the other term, well, those are two words actually, but in terms of terms, let's distribute one term, desired response. Every control system, we have a desired response. Now, what we have is that we have a group of components, yes, that work to achieve this. So in every control system, there is a desired outcome. There is a desired response. Now, having said that, let us now look at some areas that we find control systems. Right? So control systems are found in numerous forms and areas, right? And they come in different degrees of complexity. So let us start with what may appeal to you first, electrical, all right? So in electrical, the field of electrical engineering, we have control systems. We also have control systems in the field of mechanical engineering. All right. So let us now go to the softer type of field, financial systems. All right. Financial systems also incorporate feedback. So let us stick up in there for a while in terms of finance. Let's say the government has a Ministry of Finance, and we could say one of their objectives is to grow the economy. Okay, and so if the government is going to be successful at meeting that objective, then they would then put a group of, we're going to use the term group of components or a group of systems. Let me use the word system since that may be a more practical term. So a group of systems would need to be put in place that will work together to achieve this outcome, to achieve this desired response of economic growth. Okay, and earlier we had this EPOC, but I remember the EPOC project, right? And there are numerous other projects, but we have different groups that will work to achieve this economic growth. Social systems, you know, community-wise, you would want to have a certain level of social order, and so to have that desired objective achieve, then again the government, who has the responsibility of maintaining social order, would need to put things in place. Let me see if we're following through. Can somebody open your mic and tell me one system that supports social order in our local system, you know, in Jamaica?
Sir, jail, sir.
The prison system. All right, fair enough. Thank you for that. That's the reality. But it's interesting that you actually put that one first. Anything else? Social order.
Family.
All right. So, family in what sense? In what aspect? How do you see family being supporting social order? And how does the government support families in that respect? I agree with you that families do support social order. And here we're speaking about good family structure, right? Where the persons who are in charge, whether it's the parent or guardian, they will instill good principles, right? And you're right, you're quite right in that respect, that good family upbringing or good family structure supports social order. And you also have the police force, you also have community groups, yes, that will support social order. Because here it is that we want to meet. Sorry?
So you'd consider school a system to promote social order as well?
Absolutely, absolutely. Because apart from training persons for the work world, there is also the aspect of training persons how to conduct themselves in the society. So if you look at the syllabus for the primary school youths, that a part of it is instilling social consciousness, right? So that's correct. So the point I'm making here is that you have different systems working to support or to achieve the desired response. And again, with every control system, there is a desired response. It is the desired response that is now going to bring about a control system. If we should look at the biological aspect of our environment or what we see around us, take for example, the eyes. If you were to go in a room that is very dark, or it is, you know, completely dark, and then you step out or turn light on for about maybe about 5 to 10 seconds, you'll not be able to see clearly. Can somebody tell me what is happening? Those of you didn't skip biology class.
Your eyes are adjusting, sir.
I'm sorry?
Your eyes are adjusting from the darkness to the brightness, sir.
Talk to me like you're the biology man. You mean your eyes adjusting?
So the engineer I'm doing, sir, and I'm the biology, sir.
Yeah, I want you to know that this is a very important aspect to have a full understanding of all the things. Well, not just all the things, but having a basic understanding of the things around it will definitely help you as an engineer. Do you agree?
Yes, sir.
Absolutely. So I understand when you say eyes are adjusting, and that is fine. But can somebody, thank you for that, tell me what exactly is happening in the eyes as is just mentioned just now about the adjustment? What adjustment is taking place?
So does it have to do with the pupils opening and opening
Go
or
ahead.
adjusting?
Go ahead.
So does it have anything to do with the pupils, sir? The pupils.
What do you think? I want you to tell me.
Yes, sir. The pupils adjust to the amount of light.
Sir, if I may,
Yes. Thanks. I'm going to actually try to go back to Blackboard Collab so I can see the persons who are raising their hand. I'm having an issue here moving the slides. So noted. Who was speaking just now? It sounded like the name just slipped me. It was in my head here. Who was speaking just now?
Crossdale.
Crossdale, right. Amani Crossdale. All right. I'm trying to advance. Why my slide won't advance? Yes, somebody wanted to share while I try to get this to advance. Anybody want to share? Somebody was coming in before.
oh, that was an actual
So the pupils adjusting. What if the pupils don't adjust?
Sir, then
Anybody know what would happen?
Sir, too much light will enter into your eyes.
And what may happen?
Sir, can blind him.
Exactly. Damage the retina. That's the part that receives the light on the back of the eyes, right? So the body automatically adjusts to what? Light intensity. Okay. So here it is that we have a biological system. 1 second, please. So we have the body adjusting to things around us. And for example, if you were to do a couple laps around your community right now, you'd be sweating. And the reason for that is that your body is seeking to maintain a particular body temperature. Above that temperature, you may go into a coma, right? If the temperature of your body or your brain should raise above a certain point, you can lose consciousness and die. And so the body is now seeking to regulate its temperature, of course, with the use of the brain and your different senses on your skin. And so sweat is secreted to cool the body down. All right. Can somebody give me one other example of where it is that you have the body behaving in a particular way in a control system?
When you're hungry.
When who is that? Let me see if I can. Who is speaking right now?
Matthew Free.
All right, Matthew, go ahead. Tell us about when you're hungry.
Yes, sir. So when your body needs substance, the brain signals to your stomach, or your stomach signals to your brain that.
You're not sure which one. All right, sorry. Go
Not sure
ahead.
which direction. Yeah.
Okay.
You don't want signal to each one signal to. There's a signal that is provided to tell us.
I
that
agree with you, sir.
in-
I agree with you. Still, go ahead.
Yes, sir, that's it.
Okay, but you see, you haven't completed the desired. You see, whenever you state a control system, you have to know, say, what is the objective? All right, what is the desired objective? And then, you know, say, okay, what systems are working together? I don't know if I said the sweat glands in the case of the body, the sweat glands will secrete sweat, having to do with the body, the skin sensing its body temperature, sensing the temperature of the body. In the case of the eye, the retina and the iris, they are the ones working together. But here I'm trying to get us to appreciate that there's an objective and also we have supporting components. All right. All right. So fair enough, the bodies receive a signal to say that the stomach is empty. And so other things work together to address that situation, right? One other thing that comes to mind since you talk about the stomach, or yeah, the stomach. When you have a person who is diabetic, we know the pancreas is responsible for regulating the blood sugar level. And if the pancreas is not working the way it should, then the person needs to do so artificially. That is by taking insulin, if you understand what I mean. I shouldn't say artificially, but to do so manually, so to speak. They have to now take an insulin at specific time to address that problem. But under normal circumstance, the pancreas will take care of, excuse me, that situation. All right, that noted?
Yes, sir.
All right. So to just again expound on that, if persons are putting on a large event, especially when we have our Independence Day celebration at the arena, at the stadium, then if you certainly want to go there and get back home safely, and so the organizers will put into place different systems or measures to ensure that we don't have chaos and anarchy, okay? And so you have signs, ushers, you have police officers at strategic points and so on, okay? Now, in terms of engineering now, modern motor vehicles, they use electronic control signals to do spark plug timing and to meter the amount of fuel going into the engine. Even the braking, as you will see in a few slides from here, is done electronically, and that is through control systems. All right. Now, the question you'll ask is just how important, or what is the importance of control systems? So, control systems have been playing a very important role in the development of our society as we know it and how we operate today. Some of the things that you take for granted is a result of advances in control systems. Take, for example, a device that I suppose maybe everybody would have in close proximity right now. That would be your laptop or your cell phone. Maybe some of you can't recall, but a few years ago, cell phone was very, very limited in terms of who would have access to it due to the cost of it. Not only that, but the size of the cell phone was so large, it is really astonishing now to see the size and also the capabilities of a typical cellular phone. And this is a result of advances in control systems technology. And I could mention other areas of advancement, but here it is. We have improvements in the manufacturing sector, and this is perhaps an area that you can quickly perhaps relate to. So power generation, we have improvements in power generation due to control systems technology. Transportation, right? Medical care has benefited tremendously from control system technology. The military is typically the area that most high tech would start. In fact, the internet, as you may know, started in the military. It was a military tool. It was a network designed for the military, very secure network. And then it was extended to the society after some years of use in the military. And so what we're using today as the internet was once secluded or used only for military purposes. So the point here is that control systems has been and continue to play a significant role in the development of our civilization. All right. So as it relates to the manufacturing sector, which I mentioned in the previous slide, here are some of the specific benefits within that area. So in manufacturing, control systems, our control system technology has resulted in the improvement of quality, product quality. Yes, improvement in the efficiency. That is how it is that we convert raw material into the final product. Operational safety, tremendous improvement we have seen there. So in cases where we have very hazardous work environment, we now have robots working in those areas. All right, so we have now removed the human interaction from those areas and replaced them with machines. We have also benefited from reduction in the impact that manufacturing has on the environment. And here I could speak to the fact that we could reduce emissions. Yes, emissions can be reduced to control systems. And in fact, the mere fact that we're actually running a more efficient plant would be extended to the negative impact, right? Reduction of the negative impact on the environment. So we have less waste, okay? We have less waste. In relation to safety, we have the anti-lock braking system, ABS, and the electronic stability control, ESC. And these are technologies that have been employed in motor vehicles, and they have resulted in a much safer piece of equipment, a much safer mode or much safer means of transportation. All right, so there is a video that I would encourage to go and look at that explains what exactly ABS is, anti-lock braking system. And just to say a little bit more on that, it has to do with the safe braking whilst the vehicle is in high speed, all right, or in motion. Without ABS, the vehicle would have been much easier to get out of control and result in a fatal, fatality, in death, right? But with ABS, we have a much safer braking situation, and hence we're able to save life. Okay, so go ahead and look at that video at your convenience. That will explain what ABS is. Also, ESC is can be looked at. So common control systems include room air conditioning system, the washing machine, the electric oven, car engine management system, and the robotic arm that would typically be used in an assembly line. So these are examples of some control systems that you would see around you, right? I believe all the first four would have been known to each person in this group this evening. So right now I'm going to begin to look at categories of control systems. And categories of control system help us to better understand control systems and to discuss them in a meaningful way. So right now we're going to be looking at two categories: open loop and closed loop systems. Now, open loop systems, these systems, they operate without knowledge of the state of the variable being controlled, right? Whereas closed loop systems, they incorporate what is called feedback, right? They incorporate feedback, which essentially is feedback information about the controlled or control objective, all right? Two types, open loop and closed loop. Now, to further discuss these two categories, we're going to be using a block diagram to represent this system. And I did say in the opening slide that in a control system, we have what? A group of components that would be working together to achieve the desired outcome. Now, just to remind you, in engineering, block diagrams are very common, okay? And we need to understand what a block diagram is and how it is used. So first of all, a block diagram consists of blocks that we refer to as blocks, these rectangular shape units with labels on them. And these blocks represent sub-components, subsystems. The next part of a block diagram consists of arrows. And these arrows are showing the interaction between the subcomponents. So the arrows tells us how these subcomponents interact. Where does energy, where does signal, where does these signals move, and from what subcomponent to what subcomponent, okay? So that is the feature of a block diagram. Now, how it's used, engineers use these to simplify complex systems. All right, so you take a complex system and you represent it using a block diagram. Okay, so that must be clear. So here it is that we now have, the block diagram for an open loop system. There are three subcomponents in this block diagram. We have the controller, the actuator, and the plant. We'll discuss these a little later from now, but just to at least appreciate the structure of open loop system. All right. Now to the far left, we have a signal called a set point. Okay, and that is where the user would indicate the desired outcome. And on the far right, we have what we call the control variable, what it is that we are seeking to force or to have a specific value. Okay, so that is our open loop system, all right, in terms of block diagram. Let's now look at what the closed loop system looks like. So here we're seeing the closed loop system, and there are some similarities in terms of the subcomponents. We have the controller, actuator, and the plant being common to both. However, the aspect that is different is the sensor. All right, and the sensor is providing measurement of our control variable and providing this measurement for comparison with our set point. So the key feature, the key difference between the closed loop system and the open loop system is that the closed loop system incorporates feedback. All right, and feedback here is providing information about the variable that we're seeking to control. Okay, so that's the closed loop system block diagram. Now, let us compare these two systems. So for open loop systems, we see that these systems are very simple. And because they're simple, they're typically, well, they're cheaper than closed loop solutions, right? So provide a simple and cheap control solution. However, open loop systems are not suitable for systems that will experience considerable and frequent disturbance. All right, so they're not suitable for the control of systems where you have frequent and significant disturbance, and I'll explain that in a little bit. Closed loop systems now, they are more complex than open loop systems, and they're hence a little bit more expensive, or more expensive I should say, than the open loop systems. However, they provide excellent disturbance rejection, and they provide very accurate and fast response to disturbance. All right, so you may ask the question, how it is that we can achieve open loop control if we're not actually measuring, or we have no information about the variable that we're seeking to control. I often use this example to explain the situation. Take, for example, if it is that you have someone who is visually impaired and they're staying on campus, they're staying in one of the rooms, one of the dorms on campus. If it is that this individual or this student is not sharing the space, then that visually impaired person can in fact arrange the surrounding to their liking or their choosing, and they can navigate that space with little to no problem at all whatsoever. In fact, with ease. They are able to move from point A to point B without tripping or bouncing into any of the pieces of furniture. However, if it is that this visually impaired student is now sharing room with someone else who is not visually impaired, and quite likely because they're not visually impaired, they will move things around, and because they can see, they wouldn't necessarily need to put back things in the place that they were. They'll move a chair out and it may be left out of its usual place. And of course, it wouldn't be an issue for the person who is able to see. However, for the visually impaired person, they are not able to move from point A to point B as they would have in the first scenario, because we now have this space being disturbed. You now have vehicles being placed in positions that the visually impaired persons cannot identify. So the point is, a visually impaired person can in fact navigate the space from memory, yes, okay, without any problem. Hence, there's no need for measurement of or visual inspection of the surroundings. That is open loop. However, it becomes a problem for that person when the space is being disturbed, when objects are moved and left in random positions. The visually impaired person will not be able to navigate that space with ease. However, let's come now to a closed loop system where it is that a person can see. It is no issue because you can now look, see the obstacle and move around it. No problem. So the scenario I just gave to you just now is pointing to you that yes, open loop systems can in fact work. Yes, they have their places, they have their place. All right, one more example of open loop system. If it is that you have a conveyor belt system, and a conveyor belt system again is moving objects from point A to point B. If it is that you know that the number of boxes that will be on that conveyor belt is fixed, so it may be that at any given time there is going to be 5 boxes on that belt, then you can go ahead and size your drive system, that is your electric motor and your gear system, to provide the desired speed. Right? You'll match the power of the drive system with the load that is on that belt, and that belt speed will be maintained, yes, throughout quite successfully without any problems. That's open loop. There's no need to measure the speed of the belt. However, if you decide to add a 6th another box to the 5, right? A 6th box. Then what's going to happen? The belt is going to slow down, and so you no longer have the desired speed. Similarly, if you remove a box and you now have 4 boxes, then you run into a situation where the speed of the belt is going to increase. The addition or the removal, if an addition of a box or the removal of a box is termed a disturbance. And open loop systems don't do well when we have frequent or considerable disturbance. If it were that conveyor belt system had feedback information, that means you're measuring the belt speed and you can now make adjustments to the drive power, then you'll be able to maintain the belt speed in the presence of disturbance. So just giving you a comparative look at the 2 types of systems in terms of their performance, right? So again, open loop systems have their place and closed loop systems do also have their place. But I want to point out to you here also that the majority of systems in place today are closed loop. So from this slide going forward, our attention will be on closed loop systems. All right. So again, just to sort of complete this discussion on open loop and closed loop systems, examples include electric fan. The fan speed is maintained based on a switch position. There's no need for measuring the blade speed because nobody is going to be hanging anything on those blades. So it will spin at the desired speed once the button is pressed, and that will be maintained for the life of the fan until the fan decides that it is now time to retire. It will behave in a consistent way. All right. So unless the bearing in the fan becomes effective, it will behave well, or any other electrical part should go bad. Once that's not happening, the electric fan will maintain the speed as desired by the manufacturer. Okay. Toaster, electric toaster. It's designed to change the shade of bread, and by so doing, persons actually will experience a different texture to their bread. But essentially, the toast is going to change the color of the bread. Now, as far as I'm concerned, I've not yet seen a toaster with any sensor to actually observe the color of the bread and then do something. So it's open loop. So if you should take one type of bread with the same setting, you'll end up with different results. All right, so I'm going to ask to open your mics and just to comment on what I just said just now about these 2 systems. Or just raise your hands. I can now see the raise hand feature. So you can just go ahead and raise your hand and just comment on what I've just said. All right, so you're saving your comments. Feel free to raise your hand and to make a comment or to ask a question, okay? So the microwave also is an open loop system. You will place your frozen meat in there if you wish, and you press defrost. It doesn't mean the thing is going to defrost, right? It will turn off in some instances before it defrosts, or in some it might start, heating up the product to a point beyond which you intend. And so the point is that there's no measurement of the control variable. All right. On the other hand, closed loop systems, we have the air conditioner that is used to maintain the temperature of a space, a room, and that's closed loop. Electric oven, that's used for baking or cooking, does in fact employ closed loop control. The engine cooling system also employs a closed loop control system. We're now going to be looking at the components of a control system. And I said to you earlier, we saw that the open loop and the closed loop system had 3 components in common: controller, actuator, and the plant. So we're going to now look at the definition, so to speak, of each of these components. I'm going to describe exactly what these components are and what purpose they serve in the system. Let us start with the controller. So this controller here in our system is the intelligent part of the system. All right. And having intelligence simply means it has the ability to make decisions. Okay. So these decisions that the controller will make are towards corrective action. All right. So our controller is the intelligent part of the system, and it is responsible for taking corrective action to achieve the desired objective. Now, the actuator provides the effort. All right. So in each of these terms, it is good for us if we could remember at least one word or relate one word to these devices for start, and it will help us to appreciate their role in the system. So I looked earlier at controller, and perhaps you would say it's the intelligent part of the system, and by extension it does what? It takes corrective action. In the case of the actuator, we could say this device provides effort. Right? It provides effort. So the effort that we're speaking of here is the effort that is required to make changes or adjustments to the variable that we seek to control. All right. And so examples of actuators include the electric motor, and heating element would be examples of actuators. Okay. Now, the term processor plant, you could use any term. They're both the same in terms of control systems. This is, we're speaking here of the environment or the element. Yes, we're speaking to the elements within the immediate environment of the variable being controlled. Now, this might not be so clear to interpret or appreciate, but let us go to the scenario of the air conditioner. And if I should ask you, what is the variable that we're seeking to control with an air conditioner, what would you say? Please indicate by raising your hand and just share. Go ahead, Joel.
Temperature.
Correct. Temperature is the variable that we're seeking to control. Now, what do you think the plant is? So if you're in class right now on campus, and you're in one of those air-conditioned room, what would you consider to be the plant or the process based on the definition I just presented here?
Sir, classroom, sir.
That's correct, the classroom. And what do you define as the classroom?
Repeat that, sir.
What would you define as the classroom? What exactly is the classroom for you?
Sir, the area between the four walls which the air conditioner is in.
Okay, all right. And so that area, yes, and whatever is within that space would also qualify, thank you, Joel, as the, is that Joel or Jordan?
Jordan.
The last person. All right, Jordan. So the classroom consists of that space, yes, but what also is in that space would constitute the plant. So the air conditioning unit is cooling the space, which includes the desk, the chairs. If you have laptops inside there, yes, that's a part of the plant, and also the students, right, or the participants in that session. Everyone in the space. All right, that becomes the plant. So we're basically acting upon that environment. All right, you may not be aware, or some you may not be aware, but you can have a space that is not occupied by a human being, yet still it is air conditioned. And I'm speaking here of a room that houses equipment, particularly servers. These large space, very large. You'd see like I've seen a server room in New York, one entire story. And I think there were no windows, just this large concrete structure, a couple stories high, and all is in there are pieces of equipment. You perhaps have a floor where you have staff, but just housing pieces of equipment, and they have to be properly the space, sorry, has to be properly conditioned. All right, so the temperature has to be right. So the point I'm making here is that when we speak about the plant, is whatever you're acting upon. So whatever is in that space would constitute the plant. Okay. Sensor, not a part of our control system. So sensors, they provide measurement of the variable that you're seeking to control. Right? The sensors that close that gap. And I think you would all be able to perhaps recall, or maybe I'm not sure, maybe not all persons in this group did instrumentation systems. I must recognize that, and therefore most persons would appreciate what a sensor is, right? A device for converting some physical phenomena with a temperature or pH. Yes, you convert that to an electrical signal or some other signal. So you basically measure with a sensor, all right? I provide some means of measurement with the sensor. So that's the purpose of the sensor in a control system. Now, the comparator is that aspect of the control system that provides comparison between the set point and the variable that you're seeking to control. And the result of that comparison will result in an error signal, right? So the comparator looks at the control variable and the set point and provides some signal that will indicate the difference between the two, and that is called the error signal, right? Now here are two very important terms that need to be understood to better communicate what exactly is happening in a control system. So the first one is the control variable. And I've been using this term for some time, for quite a few slides now. So the control variable is the variable that we're seeking to control. It's the variable that we're seeking to force to have a specific value. Now, this could be temperature, it could be flow, it could be position, and you could list some other variables that we would need to or would seek to control. Now, the manipulated variable, yes, is the variable that is adjusted for what purpose? Is it we adjust so as to maintain our set point or maintain our desired outcome. Yes, so we adjust that variable so as to achieve our control objective. Now, can somebody give an example of a control system? And in fact, I have one right here. I want to choose a different one. So let me explain that example here, where in a conveyor belt system, for example, the one I gave earlier in the presentation, if it is motor driven, we could adjust the speed of that belt by adjusting the current, or we would then say manipulating the current in the motor, which by extension now would lead to an adjustment in the control variable. All right, so that is an example of a manipulated variable. We adjust, we manipulate this variable so as to achieve our control objective. Can someone give an example of another control system and state the control variable and the manipulated variable?
So you can control the temperature of a toaster by manipulating the current.
The current going where?
Going into the heating element.
All right, so temperature control, and we're manipulating the current in the heating element. All right, so that will satisfy. Thanks for that. I'm sharing that example. All right. Now, another terminology, disturbance variable, and I did use a term again earlier. And a disturbance variable is any variable that will cause the control variable to deviate from the set point. Any variable that will cause the control variable to deviate from the set point. And so if it is that we go back to the classroom situation where the room is air conditioned and we are maintaining a certain temperature in the room, let's say we're maintaining 25 degrees Celsius, and then you find that we are all good, we're maintaining the temperature, and suddenly a group of students came in late, they're just stepping in. We're talking about maybe 10 or 15 students coming in at once. What do you anticipate will happen to the temperature of a room? You can just raise your hand and indicate and just allow me to acknowledge you. Go ahead, Blake.
Yes, sir, it would increase, sir.
What is it?
The temperature of the room would increase.
Would increase. In fact, it would. And so the temperature is no longer at the set point, but has now deviated due to a disturbance. Now, we spoke about a variable. Here we could say that the load, maybe we could quantify the effect of persons coming in. Not just the number of persons, but it depends on also the biological state. And perhaps we could find a means to qualify. But to keep it simple, we could say the number of persons that enter the room, right? And even in fact, if they should leave the room, you may have a similar situation, right? You may have a similar situation where the temperature will be affected due to that. So whether the persons are leaving or coming in, it is a disturbance factor. Can somebody give an example of a system and what would possibly be a disturbance variable? Go ahead, Atkinson.
Yes, sir, like a air conditioned room and the door open.
Okay, a similar example to the one before, the door being open. So ambient temperature would be entering the room and constantly. In fact, that system would now be probably would never be able to maintain its objective because the air in the room is constantly leaving, and so in that case, that disturbance is very severe. But if it's open and closed, then yes, that would certainly introduce a disturbance. Can I give an example? No, Buchanan was raising hand, I believe. Buchanan, thanks for that, Atkinson.
Oh, it's okay,
Buchanan?
so I was also going to say ambient temperature using the toaster example.
Okay. What? Go ahead, Dana. Go ahead, Donna. Hello. The mic is not open, but I'm not hearing Dana Joe. While that issue with Dana is sorted out, your mic is up, but I'm not hearing you, Dana. All right, so until that is rectified. Hello. Right. So let us think, for example, at I don't know how many persons can relate to this, but if it is that you have hot water feature in your home, and if you adjust the faucets, That's the hot and the cold water adjustments to the temperature that is suitable for you. If someone should turn on, whether it's the hot or cold water pipe in a neighboring room, then you're going to find that your satisfactory temperature that you set will be disturbed. Can anybody relate to that scenario? Whether not necessarily directly that way, but the whole adjustments of the temperature of your water based on the adjustments of the temperature. I'm sorry, the setting of the faucet. Or perhaps if we are in a situation where we have, I put it this way. Go ahead, Clark.
Yes, sir. All right, you make reference to the hot water heater as well as the cold water faucet in your bathroom. And if somebody's in an adjacent, maybe kitchen or bathroom, turn on the same thing, it would be disturbed. But why would it be disturbed, sir? Why do you think you would get a different temperature?
All right, fair enough question. Can I ask, have you ever experienced that phenomena?
To some extent, but I'm just thinking, why would they? Because I'm saying if there is enough hot water there to facilitate both pipes, wouldn't the temperature remain the same?
All right. Noted, your question is noted. I'm going to present another scenario and then you can then judge from that. When you get up in the nights, let's say if you should decide to do some laundry at 11 o'clock, when you turn on your pipe, do you recognize any difference in the flow rate?
Yeah, I think it would be a lot. You have higher pressure at nights, I guess, because.
Oh, so higher pressure. Don't stay online for me. So you have higher pressure, okay? Which means what? A much greater flow rate.
Right.
Good. So in the day now, let's say on Saturday, yes, at about midday, you'd experience the opposite. You'd experience very low water pressure and very low flow rate because there are many users of the utility at that time.
So, sir, were you making reference to the pressure and not temperature?
No, I'm getting to that, you know.
Okay.
Right. So now when you have hot and cold water feature in the house or in wherever it is, and if it is coming from a central tank, when you are using the feature where you turn your hot water and your cold water faucets to the point where you are getting the type of the water to be at the desired temperature. If someone should start using the cold water in an adjacent room close by, what will that do to the flow rate of cold water?
The flow rate will decrease.
Correct. So if you drop the flow rate of cold water going to your bathroom now, your shower, what's going to happen to the temperature of the water coming through?
All right, so I get that.
You're going to have a greater portion of hot water mixing with a lower portion of cold water, so it will certainly be hotter.
I understand, sir.
Right, so that's the type of disturbance that we're speaking of. So the flow rate of the cold water is a disturbance to you maintaining your suitable temperature at the faucet. So the point I'm making here is the flow rate of water in any of those pipes, hot or cold, is a disturbance variable. And it's one that is experienced in the production, in the manufacturing plant, because when we have, there is the need for steam to carry out a number of operations in a manufacturing plant. And if it is that there are 5 stations that need to use the steam, if it is that at one point only one station is using the steam, and then suddenly all 4 or all the others just come online, you are going to have a disturbance of your control variable. And so we find that we need to have systems in place to mitigate the effects of disturbance. All right. All right, so thanks for sharing that. Now let us look at other classifications of control systems. Here we're going to look at manual control. And before I even go any further, in your reading, if you happen to see different definitions for manual control or any other term, please come back and share with the group. But I want you to take this definition and bear it in mind. So when we have our discussions, I'm making reference to this definition, okay? But please do share any other variations that you may find. Now, in a manual system, yes, let me go back to the previous slide here. Right, so this is what I should be looking at. So we have yet another classification, manual and automatic. Now, in manual control system, the intelligence is provided by a human being. Intelligence is provided by a human being. And it makes intelligence and action, right? And control action provided by a human being. Okay? Now, in automatic systems, yes, the electronic or mechanical device is responsible for decision making. So what I'm saying here is that in a manual system, the controller is a human being. In an automatic system, the controller is going to be some electronic or mechanical device. Okay? So let us look at an example. And by the way, both, and this is what I have to be careful of now, both manual and automatic systems are closed loop. You will find that in some material, depending on the context in which they define it, they will define manual systems as open loop. So remember again, it's the context in which it is defined. I'm going to give my definition and I'm going to lay the context for that. Now, in manual system, oops, what just happened here? In manual systems, like this one here, we have the level of a tank being maintained, okay? Now the operator is viewing a sight glass and he's making adjustments to a valve so as to maintain the correct level. Now, I'm hoping that you can see that there's some amount of feedback, and here, this is not electronic feedback, right? So you may find that some material might say, okay, in the absence of electronic feedback, the system is open loop. But here I'm laying a foundation to say, in my definition, once you have measurement, it doesn't have to be electronic. Once you have measurement of the variable you're seeking to control, then it's a closed loop system. So here we have a closed loop system. Why? The operator is able to inspect and make some estimation or measurement of the variable that is seeking to control. And so here it is, we have the system being closed. So he's able to maintain the level of the drum, I'm sorry, of the liquid in the drum by adjusting the valve. All right, so that's manual. Why? Because intelligence and action is provided by a human being. It is the decision being made by a human being. Now, let's look at a similar situation. We're still controlling level, but this time we're doing so what? Use mechanical means. There's a mechanical linkages. So we have a float being incorporated with a plug, right? So this is a float. I'll get my marker here, float and a valve. And if you examine the diagram, you will see that as the float goes up, the valve plug goes and blocks off the inlet. And so we're able to maintain liquid level automatically, yes, with the use of mechanical linkages or mechanical system. Go ahead, Blake. Blake has a question.
Yes, sir. So if you should compare the automatic and the manual system, sir, as it relates to accuracy and precision, sir, would you agree that the automatic may be a little bit more accurate than the manual?
Yes, generally speaking, automatic systems are more accurate than manual systems. That's general result. However, there are some very complex operations that at this point in time, automatic systems are not able to achieve that level of decision making and so on. And I said this with great consciousness of our reality, that we now have a situation where advances in artificial intelligence is way, way, way up there in terms of the capabilities of these systems. So I'm saying this with some level of reservation, but the point I'm making here is, generally speaking, yes, automatic systems are more accurate. Okay. Blake, go ahead.
Yes, sir. In the instance, for example, an automatic transmission and a manual transmission in a vehicle, sir. Let's say you're going uphill, sir. You would recognize that with the automatic transmission, you might lose power and you might demand a certain level of power to go up the hill. With the automatic transmission, you might not get that right away, but you would recognize that with a manual, you can just gear down and you get the power that you need, sir. Would you say that in some way that the manual might be a little bit better in that case?
That's one example where the manual system, in that aspect, as you put it, the manual system which has a more advanced feature, so an anticipatory feature, you are able to look ahead and then make adjustment. The system will not be able to make adjustment until it detects that the speed has gone down to a certain point. Now you have vehicles that are able to do some very interesting things, and they may be able to provide much better speed adjust, or should I say gear adjustments, that we don't even recognize that the gear is actually changing or any difference in the speed, right? So yes, you have some advanced vehicles that can in fact do that. So again, to support your point, generally speaking, closed loops or automatic systems are more accurate, generally speaking. All right, and you would see that in your reading that yes, this is one of the benefits of automatic systems, that they are not only faster, but they are more accurate, generally speaking. All right, thanks for sharing that with us. We want to now look at server control and regulatory control, two other classification. And in a server system, what we have is that the set point is constantly being updated, right? So if we're talking about cars again, the power steering, when you turn that steering wheel, the front wheels must align, yes, with the positioning of the steering wheel, and it must do so in a very timely manner. So you should not see any delays in that movement. And so the quality of a server system is how well the control variable can track the set point. For those who may be familiar with it, you guys, you watch TV and so on, and watch shows. When you look at what they call a heat-seeking missile, it's a very good example in terms of the concept. I try to stay away from military examples, but in terms of the heat-seeking missile, if there's anybody who not familiar with it, just indicates so I could change it, please. Not familiar with what I'm speaking about. Heat-seeking missiles, military technology here. Anybody? All right, so in any case, you can look it up. So the heat-seeking missile, it is deployed by one of by one of the jets. There's usually a target, and there's usually the one who released the missile. So the person who is releasing that missile has a target, which is usually another jet. okay? And every single jet aircraft that I am aware of up to this point have emissions, right? There's some amount of combustion taking place, and so there's heat. And what that missile does is to sense the trail that the jet leaves, the heat trail, and it follows it. Now, here's the point I'm making. The objective is for that missile to hit the jet. So the set point is going to be the position of that jet. Now, the position of that jet is constantly changing, yet still, the heat-seeking missile will need to constantly update its trajectory to actually achieve the desired outcome. And so we could say the control system in that missile is servo control. Okay, it's servo control. On the other hand, we have regulatory control. In this case, the fixed point, or should I say the set point, is fixed. And so the system will now seek to maintain the control variable at this fixed set point. So for example, your electric oven, you're baking a cake, you set the temperature, whatever that temperature is, maybe 120 degrees Celsius. And during the baking process, you will not be moving that temperature gauge. It will stay at that point for the duration of that baking process. And so it's a regulatory process, all right? A regulatory process. For those who may not be able to relate to the heat-seeking missile example, when we speak of robots, robotic arms are used for the packaging of goods in a manufacturing plant. And so these robotic arms, they employ motors which move the joints. So if you consider your arm, and each joint in your arm would consist of a motor for the case of the robot, right? And so to get movement, you have to be constantly changing the position of these motors to achieve the objective. And so we call these motors servo motors, right? Because they're constantly receiving new information or updated information as to where it needs to go, right? To achieve the task of pick and place, all right? Here is a block diagram of a servo control system. Note that we have the general names for these blocks, the controller, actuator, process, and we have the sensor, except that we now have specific names, right? We have specific names for our actuator. And so we have the electric motor for actuator, and we have the plant being the actual arm, right? And we're incorporating a position sensor in this example. Yet one more classification, process control. And process control is a term used to describe control systems found in the process industry. And these control systems are normally control systems that seeks to maintain temperature, flow, level, pressure, and pH, that kind of thing, okay? And let's look at a block diagram for a temperature control system. Again, I want to bring your attention to the general names for the blocks: controller, actuator, process, and sensor, right? Now, specific to this example, our actuator is the heating element, the process is the oven, and our temperature sensor is providing measurement of our controlled variable, okay? Other categories include analog and digital control systems. And today, digital control systems are predominantly used, okay? The difference is that in analog control systems, we would have incorporated the use of analog electronics, like op-amps and so on. Whereas in digital control systems, the use of microcontrollers or microprocessors are what we would use to achieve our control objective. So this brings us to the end of this presentation, an introduction to control systems. And so we would have gain an understanding as to what a control system is. As you said, it is a group of components that work together to achieve desired outcome. And we know that control systems do play an important part in the society that we live in. Our day-to-day activity is in fact impacted by control system technology. Our advances in control system technology is impacting the way we live. And if we look at healthcare, we look at manufacturing, we look at transportation, we can find areas that would have benefited from control system technology. We also looked at the categories in control systems. We looked at the open loop and closed loop system, and we looked at the difference between these two systems. We also looked at a block diagram representation for these systems, and we say that the systems, they both have elements, including the controller, actuator, and the plant. However, we must remember that closed loop systems employ feedback, which is a sensor. Some form of measurement is done of the variable that we seek to control. All right, and so you should be able to identify in every control system that you want to discuss, you should be able to identify the control variable, right? If you are unable to identify the control variable, then you will not be able to appreciate it as being a control system. Having said that, you would recognize that part of achieving the objectives include manipulating some variable in that process. So if you're at the sink and you're achieving level control of water in a jug to mix maybe some juice, then you'll be manipulating the position of the faucet to regulate the flow rate of water. And by extension, you'll be able to achieve the level of water in that jug. So we also look at different categories apart from open loop and closed loop. We looked at manual and automatic, and you would need to be able to distinguish these differences. I know persons, well, at least one person shared one of the features of the automatic system over the manual, but you certainly would need to read up on that as well. So we covered a number of things here. So if there are any questions at this point, you could please go ahead and raise them. Any concerns, any suggestions?
No.
All right, so I'm not getting any suggestions or feedback here. So if not, we will close off for today. We did the almost full 2 hours. I do advise you to read through the slides again. I will be posting a worksheet. If it's not yet available, you'll see it by tomorrow morning. You'll see the worksheet, and the worksheet will help you to bring some understanding to what you have heard and read, and will give you an opportunity to clarify any areas that need further investigation. All right, so we're going to close off this presentation. Yes, go ahead.
Just like we normally do the recording. Normally
All right,
come
guess
back
what? Yeah,
on the other side.
yeah.
I don't know, does it automatically come up on this one?
This is Trevon. Trevon, your background is extremely noisy. Could you go again with that question? Hopefully you're able to move to a different location.
I was asking, normally when we're using Moodle, the recording would normally come back up automatically. I'm asking if the recording would come back up automatically on this platform.
It will be available. It will be available. I'm not sure yet where, but it will be available. I make it available. All right. Any other question before we close off?